top it off with some hypothetical case studies, how to use these things, and then we'll talk a little bit about developments in mobile compute. Please feel free to interrupt me if you have any questions at any point in time. Happy to take them. And I believe there's also a raise hand feature on Zoom that can be used for that. So yeah, thank you. So far, I'm guessing no one has any questions about the outline slide, so we can begin. So, oh, sorry, I skipped one over. So as we all know that Gordon E. Moore predicted back in 1970s that, well, the number of transistors, which are a unit of computing on each chip, will double every 2 years. So that is in common parlance known as Moore's law. So that is still going strong in 2023. What that means is that we are able to increase the compute capacity for the same surface area of devices by roughly 2 times every 2 years. However, the recent machine learning models have seen an exponential growth in compute requirement. Think of large language models, transformer models over the last 3 years or so. So this chart is a chart by OpenAI published in 2023, which shows how much compute capacity in terms of petaflops days is required to train some of the newer models. And as we can see in the last 10 years or so, that has had an exponential increase. Now, albeit we only train the models once and we infer it again and again, the compute required for inference, which is the more frequent event, is directly proportional to the compute required for training. And it's also commonly known that any state-of-the-art model that gets released today gets incorporated into some user-facing application, which sees billions of users online within 2 to 3 years. If we look at LLMs, Bing has already integrated OpenAI's versions of LLMs, and BERT has already been integrated with Google search. So as the complexity of the techniques that went into training these AI models increase, so does the amount of compute consumed by them during inference. And unlike training, which is a one-time set of cost, inference scales with the number of users. The more users that come in, you'll be, so usually for very popular models, the inference cost within the first year exceeds the training cost by 100 folds. Now, in today's climate, most AI inference is run on cloud infrastructures, which are run on data centers. Now, these cloud data centers are limited by real estate availability. They have to be on land where they have access to cheap electricity, they have access to good network grids, and some cooling facility. Usually, they are close to water so that they can use the liquid for cooling their systems. Now, these things, these areas, these real estates are limited, and they can't double them year over year. So the way they increase the capacity of data centers is by switching out the hardware every 1 to 2 years to newer version of hardware, which in turn increases the cost of maintaining the data centers, and that is usually passed on down to the clients that use this AI infra. Now, this problem has also been highlighted in latest articles from investors such as A16Z. They are perceiving that the demand for AI compute has increased so much that it has now become a cost prohibitive thing for an AI company to go into this field without any huge balance on their bank accounts and start trying to make an AI product anew. And this is also reflected in the top 3 cloud providers' pricing. So GCP has raised prices by 50% since 2022. Azure has raised prices by 15%. And other public on-demand instances prices have really increased by 2.5%. And they're continuing on an upward trend, and they're not supposed to slow down anytime soon. So now these are the issues. Now, what are potential solutions? How can we address this so-called AI infra scarcity? So there are 3 different approaches. One is that we have better hardware. On the same footprint, we somehow manage to pass in more computations. So we'll be talking through TPUs, neural chips, and analog neural devices. And second option is we have better software. we optimize the model such that they require lower compute without losing a lot of their performance. So we'll be talking a little bit about model quantization or pruning. And the third option is something innovative, something that has not been tried before, maybe a strategy like hybrid AI. So we'll be going through that. So far, is there any question about any three of these things? Okay, all right. So TPUs or tensor processing units, these are specialty hardware that has been purpose-built for doing only one job. They just do integer 8 or float 16 matrix multiplications. And in doing so, they are a lot more efficient than any other GPU that's available on the market. Per watt basis, they can provide 10 times more performance. They can process 10 times more matrices similarly sized, by expending the same energy as compared to GPUs. So cloud variants are offered in Google Cloud and edge variants are offered by Coral.ai. Similar things happen for neural chips. So in terms of perception, we can think of GPUs as a toolbox, as a printer. And this particular application, a tensor processing unit, as a printing press with a block already installed. It does just one thing. It can only print that one block, but it does that really, really fast. And the second option, like I mentioned, was an analog neural chip. Now, just to go back in history a little bit, the very first neural machine that was built was an analog neural machine, the Mark I Perceptron. I'm sure people have heard about multi-layer perceptrons. So that is a perceptron. So that machine was using photocells to capture light input, and it was using potentiometers to adjust the so-called neural network weights. And that adjustment was carried out using electric motors, which would turn the knobs of the potentiometer to change the weights. And that was the first machine to use backpropagation. They were trying to use it to discriminate between images of squares and circles. In modern day, most of our neural network applications are digital. However, to have a throwback to this particular use case, we know that neural networks don't necessarily need to be digital. They don't need a very, how do I put this, accurate signal output. So analog signals as opposed to digital signals have a spread in their spectrum. Digital signals are more accurate, but that accuracy is not necessary for neural network outputs because they're trying to mimic the human brain, and our human brain is analog, it's not digital. So in the same vein, researchers from MIT have started using photon current-based chips to create potentially stable multi-layer deep learning chips, which can potentially be used for both training and inference for deep learning applications. And there is a different company called Mythic.ai, which has already prototyped electronic analog neural network chips. But for them, it's inference only. You have to pre-specify which particular network you want to implement in an analog device, and they'll just print that particular network. So that chip will only do that inference, nothing else. Now, the next option was a software-based option, where I was talking about quantization and pruning. Now, quantization and pruning, both these approaches essentially try to reduce how much memory or processing power your artificial neural network uses in order to provide inference. So in quantization, we take these longer numbers, this float 32 weights, and convert them to float 16 or integer 8 weights and biases. So in doing so, what we technically make use of is the fact that most GPUs and CPUs are actually faster when operating on float 16 or integer 8 operations than float 32 operations. So this reduces both the memory footprint and the compute requirement. However, when we go to pruning, this only reduces the compute requirement. What we do in pruning is, if you visualize neural networks, it's like a connection of many nodes. So you identify which are the weak connections, which are not necessary, that they don't affect the output enough to justify their existence, and we just chop them off. That still doesn't change the accuracy or the performance metric of the neural network by any considerable amount. And at the same time, it reduces our computation cost. So those are software strategies. Now, if you remember, I mentioned a third strategy, something innovative, something that has not been tried before. So if you look at the list of personal devices, in the US alone, there are around 300 million tablets, laptops, and desktops combined. So these devices also have a significant ownership in US households. Around 70 to 80% US households at least possess a desktop or a laptop. Now, why am I mentioning desktop, laptops, and tablets? So it turns out these devices have some sufficient compute capacity to carry out edge computing applications. However, they cannot handle very complex models. So that's where this approach called hybrid AI comes in. So hybrid AI is an approach in which we process AI computation on consumer's device. If it is completely doable on the device, we finish it there. If it is not, we process it as much as we can on that device, and then we move the rest of the data that requires processing to cloud infra, and we fall back on it for complicated, larger computations, and then we sync back the results back to the person's device. Now, desktops and laptops all have GPUs. They are more than capable of doing many complicated computations. Mobile phones nowadays and tablets have neural compute chips, which also enables them to handle decently complex networks. Now, I'll be showing a demo for that later. So far, are there any questions about what we're talking about? All right, then moving on. So how is that going to improve our situation? So as we can already tell, it saves cloud infra costs because we are offloading some part of the compute from cloud infra to the personal device. And it scales with the number of users that come to your application. So you don't have to maintain a steady state fallback amount of devices just to handle any peak traffic. It also reduces your dependence on network connectivity for those less complicated models that can run as a standalone model, and it lowers latency. Now, there's a particular flavor of this hybrid AI that I'm super interested in. It's the hybrid AI with model splitting. Now, what does that mean? So most machine learning models can be divided into several groups. So most of them operate serially. So you can have a first group and a second group. So in this case, what we are trying to do is split the model into two asymmetric groups, one of which has a lower computation cost. It's less complex. And we move that to the user's device. And then we take the outputs, the intermediate outputs or the activations from that less complex model, sync it over network to the remainder of the model, which is operating on cloud infra. In doing so, we are able to run complicated models on the user's data, but we are saving on data transfer latency as well as some compute capacity because we're using the user's own device to run the first part of the model. So this is a show and tell slide. Let me just go back. So I would encourage people to open up modelpubsub.com hybrid AI if you are interested in seeing it, with your own eyes. If not, I have. So Jenny, is a new page visible here? Just curious.
Yes, I can see the new page.
Okay, awesome. So I have already ran some images. So what this particular page shows us is a representation of the neural network that this page deals with. It's a image classification network. Actually, it's an image tagging network. So if you move the slider down, this is the split network. Half of it runs on the user's device, and the rest of it in the cloud. If you move it all the way up, all of it runs in the cloud. So when we run, and if you move it all the way down, the entire network runs on the user's device. So if we look at this particular image, it has been run on the user's device. So this is the very first image I ran on the device, and it took like 8,000 milliseconds to run. So it's this process spent this time loading the model up and then optimizing the model for the first run. After the model was optimized for the first run, the second run took a lot less time, 27 milliseconds. And if we look at the device and cloud split, so the split is determined in such a fashion that it's a very small download. And it's a very simple model for the device to run. So that will take a constant order time of 235 milliseconds. Now let's compare that with the cloud run. So cloud run incurs network latency, where we transfer the entire image over network. So that's one portion we are never going to change. In addition to the latency that arises from the fact that, okay, this thing has to wait in queue for other images to finish and then start running. And the entire compute consumption here is based on the cloud machine. So here it takes around 1,222 milliseconds. And no matter what anyone else tries, I believe you folks will also see similar numbers, which is not going to change much. So in this case, when we start running on device, we see an improvement in latency. The device plus cloud also shows us an improvement in latency. So that's the point I was trying to drive in here. Any questions so far? All right. So now, with that, we will come to a hypothetical application of our hybrid AI. How do we use this, for example, say in an online marketplace? So let's consider a hypothetical marketplace called Classy. And there are two applications that we are interested in replacing or aiding. One is unsafe listing filtration, and the second is relevant items recommendation. So what is unsafe listing filtration? Traditionally, whenever a seller uploads an item details to Classy, it runs an ML service server side and identifies any not safe for work content in the images. And if there is any such content, Classy denies the seller's listing, and the seller has to start over with new images. In our hybrid AI approach, our seller selects the item images in detailed creation page. And since this model, this tagging model, NSFW model runs in the browser of the seller, the NSFW images are immediately recognized as unsafe, and the seller is given a warning. Hey, this will probably not be accepted. Please change it. The seller selects a different image and submits the listing. And the listing goes through server-side validation in round one. There are no 2 rounds of validation necessary anymore. So in doing so, we saved both the seller listing time, and we saved an additional API call to the server backend because the very first entry itself was safe. Now, coming to the second application, in which we are trying to show relevant items recommendation to a person who is browsing on Classy. The usual technique for this is we get the user's past search history. We identify item category embeddings based on the recent 10 searches at whatever time point the batch computation kicked off. So these computations are done in large batches of all the users that have been active in the last 28 days or so. And then we identify top 200 or to 1,000 matches from the items database, and we store it with the user's ID. And then whenever the user logs in, we show them 25 items based on that particular recommendation, which usually is anywhere from 12 to 24 hours old. Now, with hybrid AI approach, we can look at the 10 most recent search terms stored in the browser session itself. And we can calculate the combined category embeddings, which essentially is a number that represents on average what was the user interested in. We can take those 200 items that have been calculated earlier over 1,000 items, because in practice, no one sees more than the top 100 items or so. And we can re-rank them so that based on the user's new interests, the items that are more relevant are ranked up top. And then we can do the same scroller of 25 items. Now, why is this important? It has been shown in some studies by leading marketplaces like Poshmark and Etsy that whenever you surface better recommendations real time, the amount of items that people buy increases by anywhere from 10 to 20%. So that has the ability to directly affect the top line. Now, with that, I would also like to point out that this hybrid AI approach is highly dependent on us having good amount of mobile compute. However, the mobile compute that we are currently seeing the growth of it is falling behind what Moore's law predicts. For example, this is iPhone's GPU compute growth over the years. It has around 4x, but within the same time had, so these are like 5 years. So within the same time had like Moore's law held for this particular application, it should have at least 6x or 7x. So there's a reason why mobile devices or personal devices, the compute doesn't grow as fast. It's not because the chip fabrication technology is not available. It's because they have to be very careful about thermal dissipation challenges. You are putting a source of heat right next to a lithium battery. And also that source of heat has to come in contact with your hand or other body parts in case of a laptop. So usually these sort of machines can never exceed 45 degrees centigrade. And designing better heat transfer technology has been a challenge so far. But that's where newer developments like cooling chips by Frohr Systems come in. Now, cooling chips are an interesting idea. So instead of having silicon-based chips, we have quartz crystal-based chips, which are piezoelectric in nature, instead of doped silicon. And they try to use these solid state cooling devices on very tiny footprints to usually have a cooling efficiency of 200-fold or more as compared to the fans or other conventional cooling devices used today. So potentially this has it promises to change the cooling landscape enough. They have already demonstrated in systems like AMD laptops and all that they can push 25% extra power without affecting the temperature range while still keeping it below 45 degrees centigrade. So yeah, so far that is the bulk of the presentation. So far, do you guys have any questions?